chain of events, cause and effect. We analyze what went right and what went wrong, as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. Causality is entirely supported by you. If you'd like to support us and keep the show ad-free, you can by becoming a premium supporter. Premium supporters have access to early release, high-quality versions of episodes as well as bonus material from all of our shows not available anywhere else. Just visit engineer.network/causality to learn how you can help this show to continue to be made. Thank you. By popular request for the month of May only, we're bringing back the very popular offer where you can get an additional month's discount on top of the 2 months you already get discounted for annual patrons. But it's only for the month of May. It's available for premium and above, so if you've been on the fence about supporting the show and want access to the bonus material and early episode releases, then it's never been easier. Get in while it lasts. Thank you. Bayer CropScience Institute is a community located approximately 14 kilometers or 9 miles west of Charleston, West Virginia, in the United States of America. A large multi-tenant industrial facility is located beside the Kanawha River and today is bordered by the West Virginia State University. It was originally situated there for easy access by road, rail, or river barge for the transport of raw materials in and the export of finished products out of the facility. The site was originally an airport and was called the Wirtz Field Airport. However, this closed in 1942 under World War II provisions and was converted into a government-sponsored synthetic rubber production plant that was managed for the government by the Carbide and Carbon Chemicals Corporation, in conjunction with the United States Rubber Company. Following the war in 1947, the Union Carbide Corporation, or UCC, purchased the facility and began to produce insecticides for industrial uses. And in 1986, a French-owned chemicals company, Rhone-Poulenc, acquired the agricultural division of UCC and took over operations until the year 2000. Aventis, formed by a merger of Rhone-Poulenc and AGR-EVO, or ARG-EVO, took over the facility briefly until finally in 2002, when Bayer CropScience acquired it. In August 2008, the 186-hectare or 460-acre, now a multi-tenant site, was known as the Institute Manufacturing Industrial Park, which employed approximately 645 workers across all 7 tenants, with Bayer employing the lion's share of those of about 545 in total at that time. Those tenants were Bayer CropScience, Adieso, FMC Corporation, Dow Chemical, Catalyst Refiners, Reagent Chemical, and Praxair. There are 16 production units and 5 utility and support units in total located on the industrial site, with some tenants producing chemicals that are required in part as feedstocks for other production units that are either owned or operated by some of the other tenants. Think of it a bit like this. Company A makes product A, sells a bit of that to a direct customer, but also sells a bit of that same product A to Company B, that happens to be located at the same site, and that Company B then uses it to make their own product, and so on. And then that way, companies with specific expertise in a given area, and following any strict operational licensing restrictions based on their experience, can focus on manufacturing a specific product or product type, and then the adjacent companies benefit from sourcing that locally or on-site for their own use. A win-win kind of thing. Bayer owned and operated 9 production and utility units at that time, with 2 additional process units that were owned by Adieso and FMC, but were actually operated by Bayer employees under contract. Bayer AG, or the Bayer Group, are an independently operated multinational corporation based in Leverkusen, Germany, and consisted of 3 business areas: Bayer CropScience, Bayer Healthcare, and Bayer Material Science. Specifically now, for the Bayer CropScience business unit, their headquarters are in Mannheim in Germany, and they employ over 18,000 people across 120 countries. Wow. In the United States, however, their US headquarters are located in RTP, that's the Research Triangle Park in North Carolina. Bayer CropScience, as their name hopefully suggests, is a global provider of what are sometimes described as crop protection agents, including chemical categories like insecticides, herbicides, and fungicides for both commercial and for domestic or consumer use. Within CropScience itself, there are 3 divisions: crop protection that serves the agriculture sector, bioscience that looks at genetically modifying crops, and environmental science that provides services for professional weed and pest control. Within the site, Bayer had 3 insecticide manufacturing complexes with 2 power stations, also called powerhouses, and a wastewater treatment plant. The East Carbamylation Complex, or ECC, included facilities for methyl isocyanate, or MIC, and phosgene production, as well as aldicarb and carbonyl units. The MIC and phosgene units supplied feedstock to the aldicarb and carbonyl units for the production of insecticides. The Methomyl Unit was part of the West Carbamylation Complex, or WCC, alongside the carbosulfan and carbofuran units, which were owned by FMC but operated by Bayer, and it had originally gone into service in 1983. The Adieso-owned Rodamet unit made up the third complex within the multi-tenant facility that Bayer also operated. Of specific interest in this incident, however, given all of that background information, is the Methomyl Unit, which we'll focus on moving forward. Bayer produced methomyl, both for international customers as well as an intermediate feedstock that was then used to make larvan, also known as thiodicarb, which is an insecticide as well as an oviricide, which, if you don't know what that is, it means it kills insect eggs. Hopefully it does, I guess. Methomyl is a white crystalline solid, and it has a very slight sulfur smell to it. Methomyl dust is combustible and can form explosive mixtures when dispersed in air, but then so can wheat flour. Methomyl was first introduced as a carbamate insecticide in 1966 and registered by the U.S. Environmental Protection Agency, or EPA, in 1968 as a restricted-use pesticide directly because it was highly toxic to humans. Methomyl is a chlorine esterase inhibitor that disrupts the central and peripheral nervous system. Charming stuff. For those interested in more detail about phosgene and methyl isocyanate, if any of these chemicals are sounding familiar to you, refer to the previous episode, number 26 of Causality, about the incident in Bhopal, India. The Methomyl process unit wasn't operated continuously all year round since the demand for methomyl wasn't great enough to justify it. Hence, it only ran for a few months each time and had extended outages between those production runs. How methomyl is manufactured requires a multi-stage process. First, aldoxime, made in what they call the oxime unit, and chlorine react to make chloral acetyloxime, which then reacts with sodium methyl mercaptide in methyl isobutyl ketone, or MIBK solvent, to produce methyl isoacetaldoxime, or MSAO. The MSAO reacts with the methyl isocyanate in the MIBK to finally produce methomyl. Excess MIC is then removed from the methomyl solvent solution, which is then crystallized using an anti-solvent and separated from those solvents using centrifuges. The resulting methomyl cake is dried, cooled, and stored in drums, and then warehoused ready for sale, or sent on to the larvan unit for that process to then use it as its feedstock. The liquid that remains from the centrifuge separation is what they refer to as mother liquor. It still contains MIBK, hexane, and since no separation system is completely perfect, there will be small quantities of non-crystallized methomyl contained within it as well. The mother liquor is directed to the solvent recovery flasher that separates out solvent for reuse and sends these so-called flasher bottoms across to the residue treater. The residue treater decomposes methomyl using heated methyl isobutyl ketone, MIBK solvent. So the mother liquor, which dissolved methomyl and other waste chemicals, are fed into the residue treater once it's been preheated and partially filled with solvent. Once the concentration of methomyl inside the residue treater is less than 0.5% by weight, it's then transferred to an auxiliary fuel tank where it's then mixed with other liquid waste material and reused as a fuel for one of the boilers. Focusing on the residue treater unit, the original 25-year-old carbon steel residue treater vessel was being replaced with a new stainless steel residue treater at the same time as the DCS upgrade was being undertaken in the Methomyl unit. The new unit was a 17 kiloliter or 4,500 gallon pressure vessel with a maximum allowable operating pressure, or MAOP, of 50 psi, that's PSI gauge, with a venting system designed to handle up to a 1% concentration of methomyl. The normal operation of the residue treater was to maintain a 50% liquid level and a minimum recirculation flow with the liquid contents and a heat exchanger. designed to remove excess heat generated from the exothermic decomposition of the methomyl and to maintain a 135 degrees Celsius or 275 degree Fahrenheit temperature. The heat exchanger had both a cooling and a heating mode, and during startup it used a steam line to introduce heat into the system, although operators had complained it was undersized as this took considerable time to heat up the solvent, initially at least. Once at operating temperature and there was enough heat produced by the exothermic reaction, the heat exchanger was switched out into a cooling mode for normal operation. Having said that, the temperature was also regulated by condensing the solvent vapor produced in the reaction in the vent cooler, which was then returned to solution, ultimately using the recirc loop in the cooling mode as a secondary temperature control. The decomposition reaction rate increased with increasing temperature and with increasing methomyl concentration as well. Therefore, control of both of these variables was key. The target temperature used, therefore, had to be a balancing act. It prevented uncontrolled auto-decomposition of a higher concentration of methomyl whilst ensuring the incoming methomyl decomposed rapidly so it would not increase the vessel's concentration to a level that could be unsafe. Since the plant was only run for parts of a given year, any major repairs or system upgrades were therefore undertaken during these large outage windows, including the previously mentioned Distributed Control System or DCS upgrade project. It had started in early 2006, but the actual cutover to the live system didn't begin until early 2007, and the first plant section to be upgraded was the Larven section of the Methomyl Larven unit. The Methomyl section of the Methomyl Larven unit was then upgraded during the next outage window, which was about the same time, but in 2008. The original control system was a Honeywell TDC system that was no longer actively supported by the vendor, and it was a more traditional or perhaps classic 80s-style DCS before the computer mouse had been popularized by Apple. Hence, interactions between the operators and the control system were entirely keyboard-driven. The newer Siemens PCS7 system, however, was more modern and utilized both the keyboard and mouse for user interactions. The DCS contained 3 interlock matrices, 1 for safety interlocks, 1 for operational interlocks, and 1 for control interlocks. The safety interlock matrix consisted of predefined process deviations and computer-controlled process actions that determined how and when fail-safe automatic control functions were activated. The status of all safety matrix interlocks were displayed on a color-coded spreadsheet-like table on the display console. Process mimic screens also displayed a safety matrix commonly referred to in the business as a cause and effect matrix, along with safety system status next to relevant plant component symbols. Overriding a safety interlock required a supervisor password that normal board operators did not have access to. Globally, during late 2007 and early 2008, there had been an increase in demand for Larven, and whilst previous stockpiles of the methomyl feedstock needed to make the Larven were still available at the latter half of the upgrade and maintenance turnaround, those stock levels were beginning to run low. Whilst leadership at the facility had not mandated a deadline for bringing the methomyl plant back online again, operations staff indicated that, and I quote, they looked forward to resuming methomyl production and a return to the normal daily work routine after a long unit shutdown, end quote. And finally, at long last, we have enough background information to begin discussing the incident. So let's talk about the incident itself. The very first day of the unit restart was actually Thursday, the 21st of August 2008, but those plant sections that pre-fed into the subsequent parts of the Methomyl unit aren't relevant to this incident, other than to acknowledge that a complex plant like this one takes at least a week to get fully up and running from a cold start. The original intention of the plant operators was to start up the Oxime section of the process on Monday morning, the 25th of August 2008. However, it quickly became obvious that the upgraded sections of the plant weren't completely ready for service. Some of the items they found as they attempted to get the plant up and running included: a valve had not been installed on a solvent feed line. A crystallizer centrifuge was experiencing multiple problems with electrical connections that prevented it from starting at all. A heat tracing system for one section of process pipework wasn't operating, which then led to the contents of the pipe cooling and turning completely solid, and a broken stem on a water cooling system valve on one of the vapor condensers, and that's just to name some of the bigger issues. There were actually many others. Beyond this, the new control system had yet to be tuned, with many of the closed-loop controllers or proportional integral derivative PID controllers left at their default values, leading to unstable operation if left unattended, thus requiring a significant amount of manual, human operational input and oversight by the operators. By Wednesday, the 27th of August 2008, methanol was once again being synthesized in the methanol reactor, and the crystallizers were brought back into service. The following startup stage required 2 centrifuges to separate out the methanol cake. Since the upstream process was near continuous, 2 centrifuges were normally required, one separating out a full batch whilst the other was filling with the next batch ready for the next to begin, and then they would swap over centrifuges. However, since they only had 1 centrifuge available due to the electrical problems on the other, they chose to continue the startup process using only a single centrifuge and began feeding methanol solvent slurry into the working centrifuge anyway. After the initial centrifuge separation sequence neared completion, the operators were surprised to find that no methanol cake had actually been produced. The operators at that time assumed that methanol was not actually being produced upstream, and hence why no cake was being produced downstream. During startup, it's normal practice to collect samples from various process points to confirm chemicals are correctly balanced, and a total of 4 samples of the liquid exiting the centrifuge were actually taken during this restart. Normally, the output of the centrifuge contained approximately 0.5% methanol. However, the 4 samples all exceeded 1%, with the highest one reading 4%, which was 8 times the specified operating level. However, during the startup, with the many distractions going on at the time, the operators never reviewed the results of any of these sample tests. And as a result of this, they were unaware that the solvent levels were far too high. And that was actually the reason why no cake was being produced at the centrifuge. During startup, the solvent in a storage tank is used to start the process, and via the residue treater, a large portion of that solvent is then reclaimed and returned back into the process, per the design of the system. However, the operators noted that they had consumed a reasonable amount of solvent already during startup, and it needed to be replenished soon, otherwise they would run out of solvent and the whole process would have to be stopped. They had to start the residue treater to recover some solvent. At approximately 4 a.m. local time on Thursday morning, the 28th of August 2008, the board operator manually opened the residue treater feed control valve and began feeding flasher bottoms into the residue treater vessel that was currently nearly empty. The exact amount of solvent that was already in the treater at that time was not specifically mentioned in the report, with one transcript indicating it was completely empty and another that it was practically empty, whatever that means. However, we can assume that it was far less than the 30% startup level target. In order to open the flasher bottom's inlet valve, there were 2 interlocks that needed to be bypassed. The first, a minimum operating temperature safety interlock, and the second, a minimum recirculation flow operational interlock. Technically, there was a third safety interlock for vessel pressure. However, since it was well within the required range, it didn't need to be overridden to open the inlet valve in this case. For recirc flow, that interlock had been disabled by the DCS programmers as part of their testing leading up to the restart and had not yet been reinstated. Though, having said that, the operators did have permissions to disable it had they wanted to. For the operating temperature bypass, it was common for some board operators to bypass the minimum temperature safety interlock and manually open the flasher bottom's inlet feed valve when the residue treater solvent temperature was within about 5 to 10 degrees of the target operating temperature of 135 degrees Celsius or 275 Fahrenheit. After feeding methanol and MSAO into the solvent, the exothermic reaction generated the remaining heat required to achieve the target temperature, and this was faster than waiting for the heating loop to catch up. That said, there was also supposed to be a large amount of solvent already in the tank, which there wasn't at this point of the startup, and hence the current plant state didn't come close to that practice, but the behavior had been well established in the past and was normalized at this point. With an inlet flow rate of only 340 liters per hour, that's 1.5 gallons a minute, it was going to take just over 1 full day to fill the residue treater to its normal operational level of 50%. There was no note or discussion regarding the filling of the residue treater at the 6 a.m. shift handover. As a result, the outside operator on the day shift was unaware that the residue treater had been put into operation and no further samples were taken that shift. Following the handover back to night shift at 6 p.m., At 6:14 p.m., the outside operator started the Residue Treater recirculation pump as requested by the panel operator. At that time, the Residue Treater's level was approximately 30%, or just under 5,000 litres or 1,300 gallons, with its liquid temperature between 60 and 65 degrees Celsius, that's between 140 and 149 degrees Fahrenheit, noting that this was far below the critical decomposition target temperature of 135 degrees Celsius. The vessel's pressure remained relatively constant at 22 psi gauge. At 6:38 p.m., the temperature began rising at about 0.6 degrees Celsius or 1.8 degrees Fahrenheit every minute. At approximately 10:15 p.m., the vessel's pressure, that had been steady at 22 psig since the start of the filling process, started to increase and ticked up very sharply, crossing 30 psig in a matter of minutes. At 10:21 p.m., the level was 51% when the recirculation flow suddenly dropped to zero. And then, in less than 3 minutes, the temperature reached 141 degrees Celsius or 286 degrees Fahrenheit and was climbing at a rate of more than 2 degrees every minute, noting that the safe operating limit was 155 degrees Celsius or 311 degrees Fahrenheit. At approximately 10:25 p.m., the Residue Treater high-pressure alarm sounded, and 2 minutes later the pressure had reached 44 psi gauge when the pressure relief valve opened. The pressure briefly dropped 2 psi for the next 2 minutes, but then went back to climbing again rapidly. At approximately 10:32 p.m., the Residue Treater pressure had exceeded the MAOP of 50 psig. The board operator noted this and suspected a blockage in the vent line. He contacted the outside operator, Mr. Barry Withrow, and directed him to go to the Residue Treater to check the vent system for any potential blockages, with the second outside operator, Mr. Bill Oxley, also attending to assist. The panel operator manually switched the Residue Treater recirculation system to full cooling in an attempt to reduce the increasing tank pressure. At 10:33 p.m., the temperature had now reached 150.3 degrees Celsius, that's 302.5 degrees Fahrenheit. And with the pressure now at 51.2 psi gauge, the Residue Treater vessel exploded, releasing 9,500 litres or 2,500 gallons of methomyl solvent onto the roadway. A fireball was seen on the south side of the unit, with multiple alarms sounding on the Methomyl and Larvin operator workstations. Operators began emergency shutdown procedures by closing isolation valves, de-energizing plant equipment, and activating stationary water cannons in the plant for fire suppression. Shortly after the explosion, Mr. Bill Oxley was seen struggling to walk back towards the control room, having suffered third-degree burns. The support leg bolts for the Residue Treater had been sheared off their foundations as the shell and top head of the 2.6-ton, 5,700-pound Residue Treater fell into the Methomyl Unit. The bottom head separated and came to rest about 20 feet from the Residue Treater's foundations. The explosion destroyed multiple adjacent pumps, heat exchangers, as well as electrical switchgear. Within minutes, the Bayer Fire Brigade that was stationed on site arrived at the scene of the explosion and started setting up a command post and began fighting the fire. At approximately 10:38 p.m., Metro 911 had contacted the Kanawha County Emergency Ambulance Authority, that's the KCEAA, and advised there had been a large explosion at the Bayer facility. At approximately 10:40 p.m., emergency medical services or EMS personnel began staging at the main gate of the facility. Shortly afterward, Tyler Mountain firefighters arrived on site and joined the Bayer Fire Brigade at the Methomyl Unit to assist. The fire was brought under control in the early hours of the morning. The estimated energy of the explosion was equivalent to about 17 pounds of TNT, which wasn't as big as some explosions we've covered on the show, but it was enough to do serious damage. The body of Mr. Barry Withrow, who had been attempting to troubleshoot the Residue Treater, was located at approximately 2:30 a.m. the next morning. He had died as a result of blunt force trauma as a result of the explosion. The other outside operator, Mr. Bill Oxley, who had been badly burned in the fireball, died 41 days later at the Western Pennsylvania Burn Center in Pittsburgh, Pennsylvania. Let's talk about the investigation. The Chemical Safety Board, or CSB, were assigned to investigate the incident, along with the Bureau of Alcohol, Tobacco and Firearms and Explosives, ATF, and the Occupational Safety and Health Administration, OSHA, and first arrived on site on the 30th of August 2008. The ATF concluded their investigation on the 2nd of September 2008, and they concluded the incident was not a criminal act. The CSB investigation, however, took about 6 weeks on site, but it wasn't until the 23rd of April 2009 that they released their preliminary findings, with the final report released on the 30th of January 2011, just under 2.5 years after the incident had occurred. So what went wrong? The CSB's incident summary concluded the following, and I quote, "On the night of the incident, methanol-containing solvent was pumped into the residue treater before the vessel was pre-filled with clean solvent and heated to the required minimum operating temperature specified in the operating procedure. The emergency vent system was overwhelmed by the evolving gas from the runaway decomposition reaction of methanol, and the residue treater violently exploded." End quote. Okay? Well, that's the chemistry, and I get that, but how did we get to this point in the first place? There are safety systems, operators are trained, and there are standard operating procedures or SOPs for this sort of thing, right? The safety interlocks on the residue treater unit were in place to ensure that mother liquor, flasher tails aka flasher bottoms, couldn't be introduced into the residue treater until there was enough heated solvent present first. The conditions technically therefore were, the pressure wasn't high-high, the tank's temperature wasn't high-high or low-low either, and the circulation flow also wasn't low-low. The SOP hadn't been fully updated to incorporate the newly developed HMI screens. However, it still contained important information on how to safely start the residual treater unit. One of those points was an administrative control that had to be performed before putting the residue treater Methomyl inlet feed valve into automatic. From the procedure, it states, if the tank is allowed to cool below 130 degrees Celsius or 266 degrees Fahrenheit, for any reason, it must be sampled before being heated up again. Of course, this applied not only to startup, but was also very relevant to startup. The problem was that there was no live measurement for methanol concentration via an instrument into the control system that you could then interlock against. And there's really good reasons why it needs to be a sampled, lab-tested value. But then again, even if you could provide a real-time measurement, they probably would have just bypassed that interlock as well. But either way you slice it, it was there in writing in the SOP, and they didn't check the concentration from any of the 4 samples that were taken during startup at all. So what does a correct startup sequence look like? The board operator and an outside operator manually pre-fill the residue treater with solvent to the minimum level of 30%, then start recirculation pumps. Test and confirm the methanol concentration is less than 0.5%, then start the solvent heating cycle. Normally, this is a closed-loop automatic controller handled by the DCS. The outside operator then collects another sample of the residue treater contents to re-verify the liquid contains less than 0.5% methanol. The board operator then puts the flasher bottoms inlet flow control valve into automatic, and the flasher bottoms would then begin entering the residue treater. The procedure ensures that when the flasher bottoms begin entering the residue treater, the flasher bottoms are diluted and heated such that the methanol will decompose rather than accumulate. So why did the recirculation flow drop to 0 during the startup? Well, Bayer's internal investigation revealed that, and I quote, an undocumented change in the heating-cooling control scheme was made during the control system upgrade that resulted in a flow restriction when changing from heating to cooling. End quote. So to paraphrase that, the program is screwed up, and when transitioning from heating to cooling, all the valves shut off and kill the flow completely. And whilst this is pretty shoddy, and it smacks of a lack of functional testing, both Bayer and CSB determined that even if full coolant flow had been available, the cooler could not have removed enough heat to stop the reaction, and it wouldn't have prevented the explosion. Still, not really good enough. So how did the operators override so many different things? When I was reading the report, I was curious how the DCS had its privileges set. Normally, we'll define 3 levels: operator, supervisor, and engineer, and sometimes we'll also define a 4th as an administrator, but that's not for operational use. During design and HAZOPs and PHAs, we'll look at the risks of incorrect operation and then split out set points, interlocks, and overrides based on risk. For day-to-day process settings, these are left with an operator privilege, but for anything that's a safety-related bypass, it's generally set to a supervisor level. It's an administrative control, of course, but the assumption made during HAZOPs is that operators are competent and supervisors are both competent, have more experience, and are ultimately accountable for the plant's safe operation. What's interesting here is that with Bayer's restructuring, they didn't really revisit that experience hierarchy in the control system, and I'll talk more about that in a minute. It had become a common practice for supervisors to leave themselves logged in to allow operators to bypass whatever they needed to, including safety system interlocks that became problematic when you were starting up. Without this independent and more experienced check in place, better operating practices were sometimes ignored in order to get the process unit back up and running as quickly as possible. In this incident during startup, a supervisor remained logged in to the operator matrix edit screen, and this was left active all day and all night so that anyone could defeat the control functions if they wanted to. And that's how the operators were able to override so many things so easily. I talked about an organizational change. So what happened? Between 2004 and 2007, Bayer management restructured the unit supervisory and technical oversight staff structures to thin and streamline operational costs. Traditional first-line supervisor positions for each operating unit were eliminated and replaced by self-directed or empowered teams. 4 teams of operators worked in rotating shifts, covering 2 shifts day and night, since it was a 24/7 operation, and those operator teams were supported by a technical advisor and a run plant engineer, but that was only on day shift. If they had to, they could call the technical advisor, who was on call on nights and weekends. Whilst the report doesn't specifically mention this, the wording of it suggests that these roles were actually standard work week day shift roles. I could be wrong, but it makes sense if you're trying to reduce costs, which Bayer were clearly trying to do here. So instead of having a first-line supervisor, all operators, including the technical advisor, or TA, reported to a production leader. There was a single industrial park site shift leader role, which management described as being a first among equals, who was responsible for overseeing all facility, site operations, and this was a shift-based role. Bayer described their intention for shift leaders to be, and I quote, very good operators who have worked their way through the technical advisor role, end quote. But unfortunately, this was not always true. Some of the people appointed to the shift leader role had prior experience as first-line supervisors from the previous org structure in some of the process units, but it's important to understand that their role was advisory only, meaning none of the operators reported to them. The intention of the technical advisor role, who is also not like a traditional first-line supervisor, was to be an experienced operator who worked the day shift and helped to schedule production and to provide advice to on-shift operators. A traditional first-line supervisor or a foreman had more of a work check or a looking over the shoulder sort of role, but in the new structure, this didn't exist anymore. In practical terms, the reorganization resulted in a single technical advisor being assigned to the entire Methomyl unit, working day shift and also acting as the liaison to the capital project team. The shift leader was also available to assist if needed, but in reality, they didn't work with the operators every day. Due to the scale of the upgrade project, Bayer assigned a second technical advisor to assist. That seems sensible to me. In practice, this meant that the first technical advisor focused on the larvae production, and the second technical advisor focused on Methomyl production and project support. The only problem was that this TA had no Methomyl unit operating experience at all. In interviews following the incident, the TA expressed that whilst he lacked knowledge of the Methomyl unit equipment and chemistry, he had, and I quote, hoped to learn more about the process by having a greater involvement in the unit startup, end quote. But when it came to the crunch, they weren't even able to be present during startup anyhow due to operational difficulties on the larvae unit, and they got dragged into that instead. Bayer had also appointed that specific second TA since they had experience as a technical advisor with some DCS training. Problem was, that was in a completely different unit on a completely different control system. Not exactly transferable. During the project's factory acceptance testing, or FAT, one of the more experienced Methomyl unit operators actually helped the TA. But the technical advisor remained the primary contact for the project anyhow, despite his inexperience with this particular unit. In the days leading up to the incident, the TA was noted as having worked somewhere between 15 to 17 hours every day, and when the operators were struggling to stabilize the Methomyl unit during startup, the TA had already left for the day, and they were not contacted for any assistance. Though it remains unclear if the TA could have provided much useful assistance anyhow. It has to also be pointed out that the DCS upgrade just wasn't finished. The PCS7 system was provided with 6 physical screens to display SCADA HMI information in the Methomyl unit. 5 screens were available to monitor the Methomyl process, and 1 screen was dedicated to displaying the current alarms. However, in order to operate some of the Methomyl unit equipment, operators found they needed to use 3 of the 5 available screens to have the required information all out in front of them, leaving only 2 for other plant information. In short, the HMI design required more physical screens than could be physically installed. The operators requested from the Siemens project engineers to add equipment overview screens to display multiple pieces of equipment, which are referred to in HMI design circles as Level 1 graphics. Whilst the project team had agreed to develop them, they were not ready for the startup. And whilst operators found the poor HMI design to be frustrating, they didn't see it as a showstopper to restarting the unit. When you're designing a HMI, the ground level pages are the ones you always start with, the so-called Level 3 and Level 4 displays. These have every single setting and controllable item displayed on them, so you can completely operate and commission the facility from those screens. But it's not easy if you have a large or complicated process. It comes up from time to time when I've worked with operators. We need more screens, over and again. When in fact, that's actually completely incorrect. You don't need more screens at all. You need properly designed overview graphics. Level 2, which is generally a train level, and Level 1, which is generally a unit level, and Level 0, which is your entire site facility overview. If you design your SCADA system properly, you should only need 3 or 4 screens in total, which is good since that's all that a human being can ingest at any one time anyway. And that's something I think that's worth exploring some more. There'll be a Causality Explored episode for supporters on that one. Watch for the link. So what do we learn from all of this? The CSB called out 5 root causes of the incident at CropScience, and I'll read them verbatim. 1. Bayer did not apply standard pre-start safety review, that's PSSR, and turnover practices to the Methomyl control system redesign project. 2. Operations personnel were inadequately trained to operate the Methomyl unit with the new DCS. 3. Malfunctioning equipment and the inadequate DCS checkout prevented the operators from achieving correct operating conditions in the crystallizers and solvent recovery equipment. 4. The out-of-specification Methomyl solvent mixture was fed to the residue treater before the residue treater was pre-filled with solvent and heated to the minimum safe operating temperature. And 5. The incoming process stream normally generated an exothermic decomposition reaction, but methomyl that had not crystallized due to equipment problems greatly increased the methomyl concentration in the residue treater, which led to a runaway reaction that overwhelmed the relief system and overpressurized the residue treater. End quote. Now, point 5 is actually the reason why the tank exploded, and we've been through that in detail, but I'm more interested in how we got to that point. The importance of acceptance testing, whether it's an off-site FAT sense or an on-site in an SAT or site acceptance test, is crucial. You just need to know that when you flick a switch, the system is going to work before you turn it on. Where were the control systems engineers assisting with control loop adjustments, on hand, 24/7 in case of system issues during startup? There's no mention of that anywhere. But the simple fact is, the system just wasn't ready to run yet. It just wasn't. So why the hell did they start it? Who decided that it would be just fine to fire it up? Not only that, who decided it was okay to fill the residue treater without solvent in it first? So for me, the most important root cause, which the CSB does cover a lot in the report, lays with the people that made the decision to start up, that didn't do any real PSSR, and to appreciate that it comes back to experience of the personnel making the decisions and the drivers behind those decisions. In other words, the organizational structure. Organizational structure should be subject to external review. And that's potentially a bold statement, but I'll explain what I mean. The CSB concluded that the organizational changes made at Bayer CropScience leading up to the incident was a direct contributor to the incident. A self-directed organization did not require management advice or input into the unit restart schedule. Therefore, the self-directed work teams themselves ultimately decided to just start the Methomyl unit, despite the fact that the control system and some plant equipment wasn't fully tested and the SOP hadn't been updated. After being in this structure and the shuffling of personnel through positions over time, management had become so far removed from the day-to-day operation that they were completely unaware that the operators seldom used the SOP for startups, and some of them regularly bypassed critical safety interlocks, which reinforced behaviors that directly led to the incident. Not only that, it's clear that the assigned technical advisor was not suitably qualified for the role and was not present when they should have been, since they were but they weren't dedicated to the Methomyl Unit startup. A more qualified and more experienced TA who was actually dedicated to the startup. And dedicated means they don't get dragged into other parts of the plant. They aren't allowed to be. They're dedicated. That's what dedicated means. It's common practice to have the most experienced operators dedicated to plant startup, as it's one of the most dangerous times in plant operation. And this isn't news. This is a well-established understanding. Having said that, the structure of a self-directed team plays a part in this. In his excellent book, Organizing for Safety, How Structure Creates Culture, Dr. Andrew Hopkins states that, and I quote, "Decentralized organizational structures allow profit and production to take precedence over safety." End quote. And he has said on many occasions that in certain industries, meaning those where harm can come to personnel, the public, or the environment, they should have their organizational structures regulated or approved by an independent body. Currently, this isn't the case, at least so far as I'm aware, anywhere in the world. But the thing is, the management in large organizations regularly just decide to shuffle the deck, change who reports to whom, centralize, decentralize, downsize, right-size, whatever terminology you want to use. And the issue is that the problems don't show up the next day. In the case of BP Texas City, it took several years, as it did in this case as well, before those organizational changes led to the incident. The problem is that who reports to whom drives survival instinct. If you have a managing manager that is non-technical, that you report to, and they say, get it running, you'll lean towards that as your priority front of mind. Since this person decides if you keep your job, if you get a pay rise next year, and it's a basic human survival instinct. I've watched technically excellent engineers and operators be overruled by technically ignorant managers and, well, just roll over and give up. Now we saw another example of that with the Challenger space shuttle. That's just another data point. I've also watched people that I technically respected be moved into management-first roles and watched their priorities erode over time, as the pressures of management up from above them, who are even less technical, repoint their priorities, and in effect, their promotion into management makes them worse engineers overall. Structure does actually change people. It can elevate the best of the technical decisions to the forefront, and it can also do the exact opposite, taking wonderful engineers and making them ineffective, frustrated, and perhaps shadows of their former selves. Organizational structure has to have both management and technical reporting alignment, and leadership roles should have relevant technical experience. Otherwise, they can't effectively manage their own teams and ensure safe operational procedures are actually followed. In high-risk industries, this trend of splitting management and technical knowledge roles needs to end. It is a fantasy that just doesn't work. Anyway, rant over. Let's talk about the aftermath. Despite Bayer CropScience reporting that no toxic chemicals were released because they were consumed in the intense fires, end quote, during the investigation, the CSB confirmed that the only air quality monitoring equipment that was near the unit that could detect toxic chemicals wasn't even operational at the time of the incident, so we don't really know. Therefore, there is no information available to actually know what chemicals were actually released into the atmosphere in the incident, let alone what their concentrations were. To that point, on the 16th of September 2010, Portia Gray filed a lawsuit against Bayer, alleging her son, Rayshawn Gray, died weeks after breathing dust and powder fallout from his dormitory room that they claimed came from the Bayer facility following the explosion. His dormitory room in the nearby university had its window open and was downwind from the facility, and upon Rayshawn's return to his room to shelter in place per the instruction, his room was coated with a layer of this dust. Try as I might, I could find no information on the outcome of that case. Bayer CropScience paid a total of $143,000 in fines to the U.S. Occupational Safety and Health Administration for 13 serious and 2 repeated violations from the incident following their 6-month investigation. In September of 2015, Bayer CropScience paid $5.6 million to settle violations of US chemical accident prevention laws. In addition to the $975,000 civil penalty, Bayer committed to investing $4.23 million in improving emergency preparation and responses at the facility, as well as additional protective measures against accidental discharge into the Kanawha River within 3 years of the settlement date. The plant has since been brought back into production and continues to manufacture product today. It's easy to directly blame the operators for overriding the control system and for the self-directed team for deciding it was safe to simply start the unit without any extended consultation, even though it hadn't even been fully commissioned yet. The problem is that our perception of risk can be diluted or normalized. It's because of how we learn, or one aspect of how we learn, and that's reinforcement learning. It's the same problem, the way we train machines. It has the same issue. If we're operating a system repeatedly whilst it's running, and it's running maybe 95% of the time, with only 5% of the time we're starting it up or shutting it down, there's plant trips and trip recovery, then we just get used to system operation once it's balanced and operational. The 95% of the time, that's what we get used to. And this is one of the reasons why startup is just so dangerous. It's the same equipment operated differently until you reach an operational equilibrium anyway. And that's why pre-start checklists are very important. This is why operator retraining for startups and trip recovery is so important too. It's also why independent oversight from someone technically experienced with the chemical process in question is present during the entire startup sequence, or in this case, there needed to be a set of technical leads back to back since it was a 24/7 startup over a week and a half. People plus structure plus procedures equals success. There are many causes for this incident that we've covered, but ultimately the one that worries me the most is this background, lurking root cause of many incidents like this: poor organizational structure. It feels to me like everyone has an opinion about how you should structure an organization. Who reports to whom? Matrix management, operations-led, engineering-led, safety-led, or self-led? In this case, my goodness, it never really ends. There's always a different way of saying it. There are companies out there that will come in and help you restructure based on the latest matrix, determinant, sub-self-led, whatever trendy, usually Silicon Valley-led or latest highly financially successful company. This is what they're doing. We should do it too. Usually not in the process industries though. And they get paid huge amounts of money with promises of increased efficiency and cutting costs. And if it isn't outsourced, there are those internally within organizations that think that they can do the same. But it's similar to a political election cycle kind of issue, meaning that most politicians only consider programs and projects within their current election cycle to point out and say, I achieved that in my 4 years in office, without anything that's longer term, longer time horizon generally getting ignored or overlooked. With an organizational change, it's worse than that. The people making these decisions generally exit the organization within a year or two of the change having been made, saying, see, I improved efficiencies and cut costs and made it better by shuffling people around, or something like that. But the impacts of these decisions are seldom felt in that time frame. It can take years for the problems to manifest, by which time the instigators are generally long gone and they're never held to account. There is no feedback loop, and hence they never learn from their mistakes and go on to make the same basic mistakes organizationally all over again. The problem is we have a growing body of evidence that suggests that there are organizational structures that work better and those that work worse in terms of managing risk in critical operations. When explosions kill people, we trace them back to bad design, we enact regulations, design standards, and hold people to account. They get fined, they go to jail. Punishment. When organizational change is the root cause though, we do what? Nothing? Anything? How many more incidents do we need to have around the world like this before we start taking it seriously? If you're enjoying Causality and you'd like to support us and keep the show ad-free, you can by becoming a premium supporter. We have support options via Patreon, Apple Podcasts, and YouTube memberships now as well. Just visit engineer.network/causality to learn how you can help this show to continue to be made. Thank you. A big thank you to all of our supporters. A special thank you to our silver producers, Mitch Bilger, Shane O'Neill, Jared Roman, Katarina Will, Chad During, Ian Gallagher, and Jamie Russell. And an extra special thank you to our gold producers, Stephen Bridle, Callan Frodelius Fujimoto, and our gold producer, known only as R. By popular request and for the month of May only, we're bringing back the very popular offer where you can get an additional month's discount on top of the 2 months discount you already get for annual patrons. But it's only for the month of May. It's available for premium and above levels, so if you've been on the fence about supporting the show and want access to the bonus materials and early episode releases, then it's never been easier. Get in while it lasts. Thank you. Causality is heavily researched, and links to all materials used for the creation of this episode are contained in the show notes. You can find them in the text of the episode description of your podcast player or on our website. You can follow me on the Fediverse at chidgey@engineered.space or the network at engnet@engineered.space. This was Causality. I'm John Chidgey. Thank you so much for listening.